So, this is an episode in a series of videos about artificial intelligence. In this first video, we will try to explain why we consider artificial intelligence so important and worth of study. And we try to define it exactly as it is. So let us start. What is artificial intelligence? Historically, many researchers have proposed different definitions of artificial intelligence. Some have defined artificial intelligence as fidelity to human performance, how well a machine can mimic human behavior or thought. Other authors prefer a more abstract definition based on the concept of rationality. In this case, a machine is intelligent if it can do the right thing. There is also the discussion of what artificial intelligence refers to. Does it refer to behavior or to internal thought processes? So we have essentially two dimensions, human versus rational, and thoughts versus behavior. From these two dimensions, we can derive four possible combinations. According to the selected combination, we must use different methods. The pursuit of human-like intelligence is more of an empirical science guided by psychology, involving observations and hypotheses about human behavior and thought processes. On the other hand, a rationalist approach involves more mathematics and engineering, connecting us to statistics, control theory, and even economics. We look at each one of these four approaches in more detail. But before we proceed, let us consider again the distinction between human-like and rational AI, using an example from pop culture. For example, in Star Wars, C-3PO is an example of human-like AI, designed to mimic human behavior and social interaction, while R2-D2 exemplifies rational artificial intelligence, focusing purely on problem solving and task efficiency. This construct illustrates how these dimensions influence the design and the perception of artificial intelligence, even in fictional narratives. It makes you wonder which approach resonates more with our vision of the future. Let us start by the first dimension. The Turing test was proposed in 1950 by Alan Turing. This test was designed to be a thought experiment that could answer the vague question of, can a machine actually think? A computer passes the test if a human interrogator cannot distinguish if the answers to his or her questions comes from a human person or the machine. The computer needs the following capabilities: natural language processing to communicate successfully in human language, a knowledge representation to store what he knows about the world, automated reasoning to answer questions and draw new conclusions, and machine learning to adapt to new situations and detect and extrapolate patterns. Turing considered that it was not necessary to simulate the presence and being of the person to demonstrate intelligence. However, other researchers considered that it is necessary to pass the total Turing test to interact with objects and people in the real world. To pass the total Turing test, a robot requires, for example, computer vision and speech recognition to perceive the environment, and robotics to manipulate objects and move around. These disciplines that we have talked about compose most of artificial intelligence. The Turing test inspired the creation of many chatbots such as ChatGPT, or even earlier the famous Eliza in the 1960s, which mimicked a therapist. Even though Eliza had no real understanding, many people believed they were talking to an intelligent being, showing how easily humans can attribute intelligence to machines based on language alone. The next dimension is the cognitive modeling approach. If we want to say that a machine thinks like a human, we must investigate how humans think. We can investigate more about human thought in three ways: introspection, trying to understand our own thoughts; psychological experiments, observing a person in action; or by brain imaging, by observing the brain. Once we have a precise theory of mind, we can express this theory as a computer program. If the output of the computer mimics the human behavior, the program's mechanism could be somewhat validated. There is the interdisciplinary field of cognitive science that tries to combine models from AI and experimental techniques from psychology to construct precise and testable theories of the human mind. We will not delve too deeply into this topic, even though cognitive science is an interesting field. The third dimension that we will talk about is about the laws of thought approach. The Greek philosopher Aristotle was one of the first to define right thinking, irrefutable reasoning processes. His syllogisms provided patterns for argument structure that always yielded correct conclusions when given correct premises. For example, consider that Socrates is a man and all men are mortal. We can conclude, by logic, that Socrates is mortal. These laws of thought were supposed to govern the operation of the mind of the machine, and when we started to study them, we initiated formally the field called logic. Logic, as conventionally studied, requires knowledge of certain facts about the world, which is a reality that seldom happens. We simply don't know about the rules of politics and economics as much as we understand chess or arithmetic. The theory of probability fills this gap, allowing us to reason even in the face of uncertainty. And let us go to the fourth dimension, the rational agent approach. An agent is nothing more than something that acts, from Latin agere, to do. Of course, all computer programs do something, but they are expected to do more. They are expected to operate autonomously, to perceive their environment, to persist over a prolonged period of time, to adapt to change, and also to create and pursue goals. A rational agent is one that acts so as to achieve the best outcome, or in the face of uncertainty, the best expected outcome. In the previous approach, the laws of thought, the focus was on correct inferences. Making right inferences is part of the rational agent, but there are other ways to act rationally which do not involve inference. For example, removing the hand from a hot oven is a reflex action that requires a fast movement instead of a very complicated thought process. All the skills needed for the Turing tests also allow the agent to act rationally. Knowledge representation and reasoning enable agents to reach good decisions. We need to be able to generate comprehensible sentences in natural language to get by in society. We also need learning because it improves our ability to generate effective behavior, especially in situations that are new. This approach, the rational agent approach, has two advantages over the other dimensions. First, it is more general than the laws of thoughts approach because correct inference is just one of the several mechanisms to achieve rationality. Second, it is easier to scientific development. The standard of rationality is mathematically well defined and completely general. For this reason, this approach of the rational agents has prevailed throughout most of artificial intelligence history. In a nutshell, artificial intelligence has focused on the study and construction of agents that do the right thing. What counts as the right thing is the objective that we have provided to the agent. This general mechanism is so pervasive that we could even call it the standard model. It prevails not only in artificial intelligence, but if you think about it, also in control theory, where a controller minimizes a cost function, or in operations research, where a policy maximizes a sum of rewards. Even in statistics, where a decision rule maximizes a loss function, and in economics, when a decision maker maximizes utility or some measure of social welfare. We need to make one important refinement to the standard model to account for the fact that perfect rationality, always taking the exact optimal action, is not feasible in complex environments. Sometimes we do not have enough time to achieve the optimal decision in actionable time. However, perfect rationality often remains a good starting point for theoretical analysis. The standard model has been a useful guide for artificial intelligence research since its creation, but it's probably not the right model in the long run. The problem is that the standard model assumes that we will be able to supply a fully specified objective to the machine. For an artificial defined task such as chess or shortest path computation, the task comes with a built-in objective, and therefore the standard model is applicable. As we move into the real world, it becomes more difficult to specify the objective completely and correctly. For example, in designing a self-driving car, one might think that the objective is to reach the destination safely. But driving along any road incurs a risk of injury due to other drivers, equipment failure, and so on. A strict goal of safety requires staying in the garage. There is a trade-off between making progress towards the destination and the risk of injury. How should this trade-off be calculated? Furthermore, to what extent can we allow the car to take actions that would annoy the other drivers? How much should the car moderate its acceleration, steering, and braking to avoid shaking up the passenger? These kind of questions are difficult to answer. They are particularly problematic to the field of human-robot interaction, where the driving car is just another example. It is impossible to anticipate all the ways in which a machine pursuing an objective might misbehave. There is good reason, then, to think that the standard model is inadequate. We don't want machines that are intelligent in the sense of pursuing their objectives. We want them to pursue our objectives. If we cannot transfer adequately to the machine our objectives, then we need a new formulation, one in which the machine pursues our objectives, but is necessarily uncertain as to what they are. When a machine knows that it does not know the complete objective, it should act more cautiously, ask permission, learn more through observation, and defer sometimes to human control. Ultimately, we want agents that are probably beneficial to humans. Thank you for watching this video. The next video is about the foundations of artificial intelligence. We will review the history and the different disciplines contributing to artificial intelligence. See you there!